Assalamualaikum and good morning, everyone. Okay, so today we will continue with our lectures on chapter 4. So lecture 4B regarding the steady state error for unity feedback system. Okay, so after completing this lecture, students, you guys will be able to determine the steady state error for a unity feedback system when there's a step or ramp or parabolic input, and then determine the static error constant for unity feedback system, and lastly determine steady state error performance specification for unity feedback system. Okay, so please be reminded that we focus only on unity feedback system in this lecture. Okay, so let's recap on the type of inputs. So I think this one you have seen this in lecture 3, chapter 3, 3B. So there are three types of input. So you have a step input, which has a constant value. So a unit step input will have a value 1, okay, constant value 1. And then we have a constant or a ramp input, which it is linearly changes with time. So for a unit RAM input, the coefficient of the input is 1. Okay. And lastly, we also have a parabolic input, and for a unit parabolic input, it's a half t squared. Okay, and then you can convert from time domain to frequency domain. So for step input, it's 1 over s. For ramp input, it becomes 1 over s squared. And for parabolic input, it becomes 1 over s cubed. So we focus on these three types of input and determine the steady state error. So what is steady state error? So steady state error is the difference between the input and the output produced from the system for a prescribed test input. Okay, so if you use unit step input, then you compare the value of uh, step input with the output produced from your system. Okay, as the time approaches infinity. So steady state error only applicable when your system is stable. Okay. So if your system is not stable, then the system will have no steady state error. So please remember this number 2 here. So it will be only applicable for stable system. For unstable system, there will be no steady state error. So you cannot analyze the steady state error. Okay. So there are a lot of sources that causes the error. So one of these are the three examples. So the first example, if you have a non-linear elements such as non-linear spring or dampers. So non-linear meaning that the relationship for spring is no longer F equals K times X. Maybe the relationship is different. Okay. And for damper, it's no longer F equals K times F times X dot. Okay. And then maybe you have frictions or frictions between two gears. So that are the causes of error. And then maybe the source of error depends on the system configuration. So either if you use unity feedback or non-unity feedback. And also the last source of error is the type of input that you use. Okay, so if you use unit input, then the error will be different compared to RAM or parabolic input. Okay, so let's look at an example of steady state error when you have a step input. So usually a step input will have the value shown here, the straight blue line, the top one here. So this is the should be, okay, the final value or final steady state value that the system should achieve. And your system, the output can be either output 1 here or output number 2. So output number 1 here shows that there is no error, okay, because as the time approaches infinity, then the value of output number 1 reaches the value of input, okay. So there is no steady state error. But for output number 2, there is a steady state error because it doesn't achieve or it doesn't reach the value similar to input. Okay, so for output number 1, the error is 0. For number 2, the error will be constant as the time approaches infinity. Okay, so the error is maintained the same. Okay, so if you have a RAM input, then the input or the desired outcome is the tick or the darker blue line here. And your output will be either of the three curved lines, okay? So output number 1 here, as the time approaches infinity, the error is almost 0, okay? For output number 2, there are errors because it doesn't reach the value similar to input. Okay, so output number 1, the error is 0. Output number 2, the error is constant later when the time approaches infinity. But for for output number 3, if you extend the line, then the deviation from the input will becomes larger. Okay, so the error will becomes infinity as the time approaches infinity. So you can evaluate or calculate the steady state error using final value theorem. So steady state error E epsilon E infinity equals the limit of ET when the time approaches infinity, or if you convert this into frequency domain, then it is the limit of S E of S when S approaches 0. Okay, so we look at an example based on unity feedback. Okay, so you have a unity feedback system with a forward transfer function GS, input RS, and output CS, and the feedback has transfer function equals 1. Okay, because it's unity. So E is this measured here. Is the measure of the difference between input and the feedback value. So this is the derivation. You don't need to memorize. Okay, so this is just for knowledge only. So E equals R over 1 plus G. Okay, so for unity feedback, E equals R over 1 plus G. So by using the final value theorem from previous slide, so steady state error equals the limit of S times R over 1 plus G when S approaches 0. Okay, so this is a formula that you need to remember. Okay. Okay, so R here is the input and G is the forward transfer function. So let's look at an example when you have a step input. Okay. So let's say R is a step input. a unit step input. So R equals 1 over S. So you just substitute R equals 1 over S and then find the limit. Okay, so you can cancel out S becomes 1. So the limit now only applies on GS because it is in terms of S. Okay, so 1 doesn't have S with it. Okay, so in order to have zero steady state error, okay, so if in order for your system to have zero steady state error, then the limit of GS here must becomes infinity. Okay, must be very big, so that 1 over infinity is almost 0. Okay, so limit of GS when S approaches 0 is equals infinity. So let's say your GS is a transfer function of S plus Z1 times S plus Z2. So Z are the zeros divided by S power of N times S plus P1 times S plus P2. So P are your poles, okay? So we want to determine the value of N here. What value of N? That can give zero steady state error. So here for the limit to becomes infinity, to become infinity, then N must be bigger or equals 1, okay? So in order to have zero steady state error, N must be equal or greater than 1. So meaning that the system must have at least one pole at the origin. Okay. So when N equals 1, so we have S term here, or we have pole S equals 0. Okay. So you must have at least one pole at the origin, okay, at 0. So if N equals 0, so let's say N equals 0, so we have this transfer function. Okay, so you just substitute N equals 0. So the limit here, limit of GS will be finite, okay, will have a value, will not become infinity, meaning that it will have a value. So when there's a value here, then the steady state error is not 0. Okay. So let's look at an example when your input is a unit ramp input. Okay, so Rs equals 1 over S squared. So you just substitute. Okay, so in order to have zero steady state error, so again, this limit must becomes infinity. Okay, so you substitute GS similar to previous slide. So now N must be either must be bigger or equals to, okay, in order for this limit to become infinity. So in order to have zero steady state error, N must equal or greater than 2. So you must have at least 2 poles at origin. Okay, so what happens if you have N equals 1? So you substitute N equals 1 and then find the limit. So now you have the limit to be a finite value. So if you replace N equals 0, and now the limit becomes 0. So when the limit becomes 0, then you have infinite steady state error. Okay. Now let's look at when you have a parabolic input or unit parabolic input. Okay, so you substitute Rs equals 1 over S cubed. So in order to have zero steady state error, then the limit here must becomes infinity. And using the same G, so N must be either bigger or equal 3, okay? Okay, so you must have at least 3 poles at the origin. So if N equals 2, then you get finite error. And if N equals 1 or less, you get infinite error, okay? Okay, so don't worry about too many terms here. Later on, I will summarize in a table, okay? So now let's look at static error constants. Okay, now just now I explained about the steady state error. So for step input, the steady state error is 1 over 1 plus limit of gs when s approaches 0. So for RAM input, it's 1 over limit of s times gs when s approaches 0. And for parabolic input, it's 1 over limit of s squared times gs when s approaches 0. So this is the formula to find steady state error for a given input, okay? So here you can find the static error constant. So the static error constant basically is the limit here, is the value of the limit. Okay, so for the position error constant, Kp equals the limit of g when s approaches 0. For the velocity error constant, it's simply this one, okay, when g multiplied by s. And lastly, for the acceleration error constant, it's when g multiplied by s squared. Okay, so now you have 6 additional formulas that you need to know, okay? You have the steady state error for each of these input, and you have the static error constant depending on the limit that you use to calculate the steady state error. Okay, so this is the summary that I told just now. So Kp and the steady state error is 1 over 1 plus Kp. Okay, so the first one here is for unit step input. The second one here is for ramp input. And the third one is for parabolic input. Okay. So the static error constant can assume or can have 3 values, either equal 0 or equal a constant or finite constant or equals infinity. So each of this value will give to a different steady state error. Okay. The value of steady state error decreases as the value of static error constant increases. Okay, so please for now remember the formula given in this green box. Okay, now let's look at the type of system. Okay, just now we have the value n here. This n, okay. So this n here actually represent the type of system that that the GS possess, okay. So let's say you have GS equals this transfer function k times s plus z1 times s plus z2 and so on, divided by s power of n times s plus p1 times s plus p2 times and so on, okay, for a unity feedback system. So look at this s power of n. So you have a system type depending on the value of n. So if n equals 0, then your system type is type 0. If n equals 1, then the type of your system is type 1. N equals 2, it's type 2, and so on, okay? So n here represent the system type. So let's look at an example of type 0 system. Okay, so this is the a transfer function given. So here, s power of 0, so it becomes 1, okay? S power of 0 becomes 1. So here the system is type 0. So let's say the question asks you to evaluate the steady state error constant and the steady state error for step, ramp, and parabolic input. So when RS is a step, ramp, and parabolic input. So firstly, you calculate Kp. So Kp is the limit of GS So you just substitute GS and find the limit when S approaches 0. So you get Kp equals 5.208. Okay, so you just substitute S equals 0. And then find the steady state error during a step input. So 1 over 1 plus Kp. So you get 0.161. And then next, under a ramp input, you calculate Kv. Okay, so it's the limit of S times Gs. So S times Gs. So when S approaches 0, so you get the limit equals 0. Okay, because you have S here at the beginning. And then find the ramp input steady state error, 1 over Kv. So the steady state error is infinity. And lastly, when the system has a parabolic input, so you find Ka. So you have S squared at the beginning here. So you get Ka equals 0. So similar, the steady state error for parabolic input, it's infinity. Okay, now let's look at a type 1 system. So let's say you have this GS. So S equals S power of N. So N equals 1. So you get S at the beginning here. So similarly, find the steady state error for the three types of input. So first for step input. So you just substitute S approaches 0. So here you get Kp equals infinity. And then the steady state error is 0. And for ramp input, steady state error becomes 31.2.25. No, for Kv. And the steady state error for ramp input, it's 0.032. And lastly, for Ka, you get equals 0. And the steady state error is infinity. Now, if you look closely for the type 1 input, if you have a unit step input, then the system will have no steady state error. Okay, 0 steady state error. But if you use a ramp input for a type 1 system, then the system will have an error of 0.032. Okay, so for type 1 system, it's better if you use a step input. Okay, so because it will produce 0 error. And now lastly, let's look at type 2 system. Okay, so S power of 2. So same thing, you find Kp, Kv, and Ka. Now, if you look closely for a type 2 input, if you use step or ramp input, the steady state error will be 0. But if you use parabolic input, then the system will have an error. Okay. So to summarize all this, so for a type 0 system, a unit step input will produce a error for type 0 system. For type 1 system, 0 error for step input, and also type 2 system. For ramp input, type 0 system will have infinity error, and for type 1 will have a constant error, while type 2 will have 0 error for ramp input. And lastly, for parabolic input, a type 0 system will have infinity error, a type 1 will have also infinity error, and for type 2 we will have a constant error. Okay, so that's basically about steady state error. Okay, so it depends on the type of system which is this n here, s power of n. Okay, so each for type 0, type 1, and type 2 has a different steady state error depending on the type of input that you use or you apply to the system. Okay, so this formula is important for chapter number 5 later, where we want to design a system or a controller uh, based on some requirements. Okay, maybe a system that you want to design, you want to have a, a constant error. Okay, you want to have a constant error, and at the same time you want the system to have no overshoot, for example. Okay, but it's like pros and cons. If you want a system to have no overshoot, then the system must have a little bit of error. Okay, a little bit of steady state error. If you don't want any steady state error, then the system probably have a little bit of overshoot, something like that. Okay, so it's hard to get everything that you desire, but later on in chapter 5 we will learn on how to design a system according to a specifications. Okay, okay, so let's look at an example. So let's say you are given gs equals 1000 times s plus 8 divided by s plus 7 times s plus 9. So evaluate the steady state error constant and the steady state error for step, ramp, and parabolic input. Okay, so firstly, before we can evaluate the steady state error, we must need to remember that um, to evaluate a steady state error for a system, the system must be stable first. Okay, so for unstable system, there will be no steady state error. Okay, so first we need to evaluate the stability of the system using RH criteria or Raut-Hurwitz criteria. Okay, so let's say this is a unity feedback system. So first we need to find the closed loop transfer function first. Okay, so using unity feedback system, so gs over 1 plus gs and substitute for gs, so you get this closed loop transfer function. So again, for Raut-Hurwitz criteria, you use the denominator. Okay, okay, so we use the denominator, we generate the table, route table. So start with s squared and then s1, and then fill in alternatingly, and then find s naught. So if you look at the first column, there are no sign changes, meaning that all poles are located in left half plane, and also the system is stable. Okay, the closed loop system. Then after that, we can analyze the steady state error because we know that the system is stable. So this is a type 0 system because n equals 0. So you use the table for type 0 system. So calculate Kp. So you get 127. And the steady state error for a step input, you get 7.8 times 10 power of negative 3. And then for the remaining input, ramp and parabolic input, the error is infinity and the static error constant are 0. Okay, so you don't need to calculate, just refer the table. Okay, any question before we proceed to the next example?
No, sir.
Okay, let's look at the next example, example number 2. So let's say you are given a specification for steady state error, a system that maybe you want to design a system to have KV equals 1000. So what we can derive from this, if we want a system to have KV equals 1000, so we know that the system is stable because it has a value of KV, and then the system is type 1, okay? Because if you look at the table that I gave previously, so if you have a KV constant, so it's a type 1 system, okay? Because type 0, KV is equal 0, and type 2, KV is infinity. Okay, so the system should be a type 1 and a stable system and a type 1 system. And then you must use a ramp input to test, okay, to test the system. And then the steady state error is 1 over KV. Okay, so this is these are the information that you get if you are given this specification. Okay, so from here you can maybe design a transfer function suitable according to this criteria. Okay, and lastly, let's say you are given this transfer function. So find K so that the steady state error is 10%. Okay, so how to find K? So firstly, we need to evaluate the system type. Okay, so the type of the system is type 1. Okay, because S power of n equals 1. And then for type 1 system, we have Kp equals infinity, Kv equals constant, and Ka equals 0 from the table. And we have the steady state error. Okay, so we want a 10% steady state error. So meaning that we must use ramp input, okay? Because if you use step input, then the steady state error is 0. And for parabolic input, the steady state error is infinity. Okay, so if you use a ramp input, you get Kv equals 10. Okay, so reverse the process. So Kv equals 10. So you find the limit of Gs. So from here, you get K equals 672. Okay, so dia macam reverse lah. Dah ada jawapan, kita reverse kan untuk dapatkan K. Okay, after you get K, then you check for the system stability, whether this system is stable when you give this value of K. Okay, sometimes when you give this value, the system is not stable. Okay, so you need to check for stability after you find the value of K. So if it's not stable, then you cannot get the steady state error 10% for this system, no matter what you do. Okay. Okay, so that's it. Any question before we end this lecture?
No, sir.
Okay, so what I want you to do now is to um, uh, remember this table. Okay, table that I that mentioned about the different types. Okay, so please understand this table so that later in chapter number 5, we will use this again. Okay. Ya, ada soalan?
Sir,
Hmm.
untuk yang example satu tadi, Yang ni dia ada bagi TS sama dengan GS over dengan 1 tambah dengan GS. Tapi yang untuk yang soalan example 3 tadi dia tak ada pun ke lain?
Example 3 ni dia guna limit ni. Yang ni tadi kita cari TS sebab kita nak tentukan dia punya system stability dulu. So kalau nak determine system stability, kita kena guna closed loop transfer function. Kita tak boleh guna GS. Sebab system stability kita kena simplifykan block diagram tu dulu. So kita assume yang ni unity feedback. Okay? So unity feedback yang ni. Gambar ni tadi. Mana jauhnya? Ni. Ni unity feedback. So kita ada GS kat sini dan unity feedback. So sekarang ni kita punya analisis terhadap unity feedback saja. Okay? So bear in mind lah kita dalam unity feedback. So untuk determine stability, kita kena simplifykan block diagram ni dulu untuk cari stable ke tak sistem. Whether the system is stable or not, we need to find the closed loop transfer function. Okay. So after you determine the system stability, you know that the system is stable, then you can do the analysis of steady state error. Okay, so it's different from example 3. Example 3, we know that this is GS, the top one here. So we want to reverse the process. We want to find KV. We want to find the value of K. We reverse the process. We use limit. So the limit is terhadap GS only, not TS. And then we use that to find K. And then after you find K, you repeat the Rapp-Hurwitz criteria to check the system stability. So to check for system stability, you need to find TS kat sini. So find TS using unity feedback and then generate the Rapp-Hurwitz table to determine whether the system is stable or not. Okay?
Okay, sir.
Maybe you can do this by yourself. Check the system stability by finding the TS and do the Rapp-Hurwitz criteria. Okay? Sepatutnya nak buat ni tapi tak larat. Okay, so that's it for today's class. If you have any question, you can ask me through WhatsApp, okay? Or just a reminder, okay? So some of you asked me through WhatsApp, but didn't introduce yourself. So usually I will ignore anybody that didn't introduce yourself. Okay, so there are a few people, okay? So I just ignore, okay? Please introduce yourself properly, okay? So don't suddenly WhatsApp, hello sir, I want to ask question. So I don't know who you are, so I usually ignore, okay? So don't be sad or angry if I ignored your text, okay? Or just blue tick, okay? So see you guys on Monday. We will do tutorial related to steady state error. Thank you. Assalamualaikum and goodbye.
Thank you, sir.
Thank you, Doctor.
Thank you, sir.
Thank you, sir.
Thank you, sir.